Hello, everyone. My name is Chandru Mullaparthi. I'm a software architect at Bet365. A little bit about me. I've worked in the telecoms domain since 1995. I've been working with Erlang since 1999, and currently I work for Bet365. A little bit about Bet365. It was founded in 2000. It's a privately held company located in Stoke-on-Trent in the UK. It's the largest online sports betting company, both in terms of number of customers and revenue. We have over 19 million customers. It's one of the largest private companies in the UK. I think currently we are at about 2,500 people and about 300 odd in the technology department. Just an interesting stat, in 2014-15, I think about 34 billion pounds was staked in gaming. So it sort of gives an idea of the amount of revenues and traffic flowing through the systems. And it's a very technology-focused company. But yeah, actually, before we dive in, I have a small request from the audience. If I crack a joke, can you please, and you like it, can you please laugh loudly? Because I'll tell you the reason. Earlier this year, I presented at the EUC. So that was recorded, and I have a 9-year-old son he's into programming. So he watched my video and said, oh, it was really nice. I showed it to my friends. It was a bit awkward when you cracked a joke and only you were laughing. Because I think the microphone was only catching my voice and not the audience's. So just so I don't have to face that comment again from him. Right, so let's dive right in. So this talk is about basically what not to do so that you end up waking at 2 in the morning because you're being called out. Erlang, as some of you, if you're using it, is quite powerful, so you can do a lot with it, but you can also build a system which goes horribly wrong, so you get called out at odd times. So firstly, starting with message passing, that's what, it's a selective receive, as we call it. You can choose what patterns you want to handle at any one point, and so it simplifies writing your code. But if the incoming message rate is greater than the speed of execution of each message, well, queues build up. And one of the last things you want to do in an Erlang system is have a process building up message queues, because generally after that, the system becomes sluggish and hard to recover. So yeah, one of the fundamental principles is when building an Erlang system, do not allow large message queues to build up a process. The reason is once your the message queue is large, depending on how you've written your code, you could end up, every time you're looking for a message in a message queue, you could end up scanning the whole message queue, which can take a long time if it's big. Also, Erlang has this feature that if a process has a large message queue and another process is trying to send a message to it, it incurs a reduction count penalty. A reduction count is basically, if you like, it's like a time slice. Every process spawned within Erlang gets a 2,000 reduction quota, and each reduction roughly corresponds to a function call. But if it sends a message to a process which already has a large mailbox, it gets a penalty. That's Erlang's way of coping that, slowing down the system so the process which has a large message queue can catch up. So one way to reduce message queues in your system is to actually suppress unnecessary messages. Now, this is an example of, say, what a simple server might do. So you have a message handler, and it's doing a receive clause. So there's a message coming in, which is the tuple in from a message, and what it does is it it spawns another process to handle it and goes back into its receive queue. It does a spawn link because it wants to know when the process has ended or if the process has terminated abnormally. And the spawn process starts at the worker, it does something and sends the result back to the parent, and the parent then sends the result back to the caller. Which, this is a fairly straightforward way of writing it, which is fine, it'll work. But the problem is for each incoming message, if you count how many messages you're passing around, so there's the message coming in, which is the task to do. You're spawning a process. It does something, it sends the result back to the parent process, so that's 2 messages. And when it dies, because you've spawn linked, it sends an exit signal. So that's 3 messages being passed for each task you want to do in the system. Which is fine, again, if you're handling hundreds of messages a second, or maybe even a couple of thousand a second. But if you're handling tens of thousands of messages a second, instead of 10,000 messages a second, you are actually within, the system is dealing with 30,000 messages per second within it. So another way to write that is, again, there's a receive, and you just spawn the message, but, you spawn the process, but along with the data required to execute the task, you tell it who was calling it. And within the spawn process, which is the worker, that's where you can detect any crashes and then call the error handler from there and send the result directly back to the caller. In this particular case, there's only one message you're handling. Okay, the send result is common to both, so if you compare the first and the second version, the first version has 4 messages being passed around the system for a single task execution. The second one, there's only 2. And like I said, for moderate loads, this is not a problem, but if you're handling really high loads, this is unnecessary work, and if you can cut down on it, you can get better capacity out of your system. One thing to be aware, so there's a number of ways you can spawn a process. So there's a spawn link, which are BIFs within the Erlang module, but there's also a module called proclib, where you can spawn a process. But what it does is it's very convenient when you're developing a system, actually, because if a process crashes, a process which is spawned using proclib crashes, you get a nice error report. But the error reports are sent to what's called the centralized error logger, and the error logger is really bad at handling a high volume of crash reports. So for instance, say your system's running at a high load, you're handling tens of thousands of messages a second. Someone's introduced a new configuration item, which actually then starts crashing every process which is being spawned, because either your configuration is wrong, it's unexpected. Now suddenly you're generating tens of thousands of crash reports a second. And that's one way to very predictably kill your Erlang node. So proclib's nice when you're doing it during development, but I'd never use it when in code, which is running at handling high volume of messages. Another nice trick, so the reason message queues cause problems is because the receiver of a message has no control over the sender. Anyone can send a message, and there's nothing I can do about it. So in such cases where you want to make sure that a consumer is not overloaded by producers, say because of traffic spikes, maybe your regular traffic patterns are pretty predictable and your system can deal with it, but if there's an unexpected spike of messages and you want to be able to deal with it without killing the consumer process, say. One way to do that is get all the producers' messages into an ETS table and let the consumer pull messages off it, so that if there is a temporary spike of messages from the producer, the consumer can still keep working at its usual pace, and your system can behave in a stable manner. Overload control is again, my background is mostly in telecoms, and one of the biggest requirements there is that the principle of graceful degradation, that if you get a traffic spike, you don't suddenly die and then restart, but you continue running, but maybe with a certain level of service degradation. So if your normal traffic levels are X and suddenly you're getting 5X, even if you can handle 0.8X of your traffic and still reject the rest of it, that is still better than coming to a complete halt and causing an outage. So there's a built-in overload control module within Erlang, which I would suggest take it as an example implementation. It's not really suitable for production use for a number of reasons. Firstly, it's implemented as a gen server. So basically, the way it works is you're sending it a message saying, can I handle this? Now, the ironic thing about it is if you've got a traffic spike, you might end up actually overloading this particular server, the one which is your gatekeeper. So yeah, I mean, it's not really suitable, and there's a lot of extra message passing as well. So every time you want to make a decision on should I accept this next request or not, you're passing 2 extra messages. And again, like I said, when you're dealing with very high load, that's amplified. And it again caters for global load within the Erlang node. It's not interface specific. If your Erlang node has, say, 3 or 4 different interfaces, the cost of handling a message from a certain interface might be a lot more than the other. So, some interfaces you can handle thousands of requests a second, but some of them are more expensive. You can only handle hundreds of them. So you want to set different limits for each one of them. But it's not actually that hard to roll your own overload control, and that too interface specific. That's really a very simple example of how one might write an overload control module. It's named NPS, which is number per second, how many you're willing to handle. And all that it does is basically every time you ask it, can I handle this request, it's sort of checking how many requests have I already handled in this particular second, and it gives you a verdict of either allow this or deny it. And you can have multiple instances of it. And the way it roughly works, there's a test being shown there, which is if you set it to say, I'll handle 10 per second, and you make it handle 15, you can see the first 10, it'll give a verdict of allow, but the rest of it it'll deny, and it's quite cheap to implement. So there's no message passing involved. It's just, as if you don't count how the time is being generated, and if figuring out the current time is not an expensive operation. Native RPC, again, native RPC is the RPC in Erlang is a big feature of it. It works, but again, it has its problems when you want to use it at high load. This is a description of how 2 nodes connect to each other the first time they want to talk to each other. So there's something called EPMD, which runs alongside every Erlang node. There's one instance of EPMD on every host, regardless of the number of Erlang nodes you have. EPMD stands for Erlang Port Mapping Daemon. And basically, a node, the A at host 2, when it comes up, sorry, is there a pointer? No, it's fine. I'll just point. So if A at host 2, when it comes up, it connects to its local host on port 4369 and says, yep, I'm listening for connection from other Erlang nodes on port, say, a random port. Thanks. And if another node called A at host 1 wants to connect, the first thing it does is it figures out that host 1 is what it needs to talk to again. It connects to the well-known port 4369, and then asks the question, well, where is node A? And EBMD says, well, node A is listening on 2200. It connects, checks cookie, and connects, and then you can have RPC working. And native RPC works a bit like that. Sorry, can people at the back see it? Sorry, I didn't realize the room was that deep. So basically, what happens is when you do an RPC call, a worker process is spawned, which then does a gen server call on a well-known process on the remote node, which spawns a worker process. It takes care of I/O. For example, if your code being invoked here is printing to the console, the native RPC actually takes care of sending that back to you as well, which is kind of which is not what you want really when you are executing a system under high load. So, I mean, I guess the point I'm trying to make with this slide is that native RPC, while it works well, actually it does a lot of wasteful processing. And the bigger problem actually is that is the well-known process here called Rex. Every RPC call coming into this node ends up as a message on this. So you can imagine what happens if a number of client nodes all want to talk to the same server node. And we've had this in production a few times at AE where this process used to build up a huge message queue. This is a problem because not only is your RPC calls going over it, actually if you're using amnesia in replicated mode, that is, any amnesia operations are also backing up here. In the same way, the way Erlang nodes detect whether they are sort of working well or not is again a heartbeat message over the same interface. Again, they start backing up, and suddenly your whole node becomes unresponsive because this process is becoming a bottleneck. And it's not just the incoming messages, really. So you see what it does here. It does a spawn monitor of a worker process. And this one, not only does it get a reply back, but when this process dies, it gets a down message as well. So in effect, for every incoming message here, there are 2 messages going back. So every RPC call results in 3 messages being handled by this Rex process. So, as I mentioned earlier, there's the head of line blocking problem. If messages are getting backed up and say one of them is actually, one of your RPC calls has generated a massive response, all of that has to come down that single socket, and your rest of your operations are getting backed up behind that. So we implemented our own RPC mechanism, which was quite simple because we didn't want some of the wasteful stuff which is in the native implementation, which is it would set up its own socket connections. I mean, I've just put Rex over here just to illustrate how you could modify the native implementation to make it easier, but we had our own implementation. It was our own application. And all that it did was it basically It would look up a socket, a connected socket for that node. It would insert a request ID and the calling process's ID into that, and directly send a message over the socket. The receiving and all that it does is it takes one message at a time, spawns a process, and lets that spawn process do all the work. And when it's finished, it sends the result back directly on the socket. So actually, this particular process is not really doing much. And actually, this implementation gave us a lot of stability in terms of handling. So we left the native RPC connections just for Amnesia to do its replication. So it improved the stability of our node. And the advantages are that suddenly now that you have control of that socket, you can introduce overload control into it so that the server side has control on how much it's handling and can reject it. You can use a different transport protocol. Instead of using TCP, you can use SCTP if you want. And you can have a clean load balancing. You could use multiple connections. And yeah, the side effect of using multiple connections is that you can avoid the head of line blocking problem, because if you know it's an expensive request or the response is going to be large, you can actually send it down a different connection. This is another thing with Erlang that generally, at least in my experience, what I found is that it's much harder to implement long-lived stateful processes because you have to, there's a lot more to think about, the state to manage. And if the state of that process becomes especially large, there are garbage collection issues. Well, garbage collection is per process in Erlang, but still, if the state is big enough, the pauses can become significant that, and again, if garbage collection takes long, you get a higher reduction penalty, which means you're contributing to, again, message queue buildup. And message queue buildup, again, is the Achilles heel of Erlang. It doesn't recover well from it. And generally, if you've got a long-lived process, you want it supervised. So, and again, you have to put in more effort to make sure that you get the correct supervision strategy. So, I mean, it's hard to avoid long-lived stateful processes. But generally, the rule of thumb is if you can design it in a way that actually most of your work is being done in short-lived processes and your long-lived processes are simple, then the chances are you can get it right easily than long-lived, complex, stateful processes. So the next thing is a bit about Amnesia. There's recently a long thread within the mailing list about, is Amnesia suitable for the job and stuff like that. So, well, Amnesia is a built-in key value store within Erlang. It supports ACID transactions, and it supports real-time replication of tables. It allows you to have 3 types of tables. RAM copies, as the name suggests, the table only exists in RAM. Disk copies is basically the table is held, a copy of the table is held in memory, but it's also persistent. And disk-only copies, it only exists on disk. And the way Amnesia manages tables, for each table, there's a file on disk with a .dcd extension, and that's where all the data for it is stored. All modifications to persistent tables are written to a file called latest.log. That's like a write-ahead log, basically. And occasionally, the contents of the latest log are written to table-specific log files, if you like. And when I say occasionally, again, that's controlled by configuration parameters, but that's the idea. And occasionally, when the DCL files become about 25% of the actual size of the table, then the entire contents of memory of that table are dumped to disk. That should sort of give you an idea of where the problems occur with Amnesia. The way it does table management can cause amnesia to be overloaded if you've got a write-heavy application. Because every time the number of changes on a table is about 25% of the size of the table, it takes the entire copy of what's in memory and dumps it to disk. And if your table is very large, it can take time. The bigger problem, though, is that amnesia doesn't really deal very well with net splits. It's when a net split occurs between a replicated amnesia cluster, basically the only way to resolve it is to restart one of the one or some of the nodes, and they copy they copy the latest copy of all the data in a table from another node, which is believed to have the latest data. Now that means data loss, basically. Every time you have a partitioned network within amnesia and you've got writes going to both nodes, the only way to recover from that is restarting one of them, and you lose the writes done to one of the nodes. There is an open source contribution from Ulf Wieger, which can do the unsplit for you, but again, it doesn't really work well for large tables. So just to give you an example of a use case where amnesia worked really well. So whatever I've said is not to say that amnesia is not fit for purpose, but it's actually there are certain use cases where it really shines, and it's hard to beat it. But there are some use cases you really shouldn't be using it for. So for instance, within EE, we had this customer database of about 80 million records. But the main characteristic of it was that it was read-heavy. We would probably have about 500,000 writes to that database in a day, but it would probably handle something in the region of 500 million or 750 million reads a day. So there's a huge skew between the two. And we had a single provisioning node as well, so that all the writes used to come into a single DB node. And that was controlled manually by the operations team, which means that if we ever had a net split between the two database nodes, they knew exactly which one to restart. And the bottom are all the client nodes there. And what we did was, well, that's your shared amnesia cluster. What we did was we put what are called database interface nodes, and these exposed various protocols like LDAP and RPC and HTTP. But between the DB nodes and the DBIF node, we had our own RPC application, which I talked about earlier. So what they did was, well, they used to load balance, read traffic across the two, but if one of them had to be restarted, like say to resolve a partition network, none of the clients would know anything about it, because the RPC application we had would immediately detect the loss here and just redirect all the traffic to this. And because amnesia is really, really good at serving read traffic, none of the client systems ever really noticed that we had a problem in replication there. So in read-heavy scenarios, amnesia really, really shines well, regardless of the size of the tables involved. Well, I say that, but I don't know if I'd put 1 billion entries into it. Where it didn't work, I mean, this went quite badly wrong. So this was basically our system which controlled data policy on the network. This is actually very simplified. So these are our core network elements, like our packet gateways in the mobile network. And there's a bunch of protocols which come in here, and this is basically every time you fire up your phone and you're using it, you're consuming data. These are sending signals about how much you're using. These would basically decode the protocols coming in, normalize the data into an internal format, pass it on to the core processing nodes, which again would interface with a bunch of external systems. Again, talking various protocols. And ultimately, well, that's storing customer usage data, saying, how many bytes have you used? What's your allowance per month? Or what's your current allowance if you bought a data pass, for example? So this architecture was really good. I mean, it started off really well until we started getting traffic spikes. Now, what happens is if, say, a base station or something went out, lost power or whatever, suddenly a whole bunch of customers would migrate to another base station, and you get a signaling spike. Now, depending on how far up you move in the radio network, if you've got a packet gateway which restarts, you're potentially talking about 500,000 customers moving on to the next packet gateway, and all of them trying to reestablish their data sessions at the same time. And that causes a huge spike, which is fine. I mean, we had overload control, which I described earlier, on all these edge nodes. We knew how many we were letting in. But still, at a certain point, what would happen was Amnesia would start getting overloaded over here, and that would take a long time to resolve, because this was being used in a write-heavy and a read-heavy fashion. And that is a use case which Amnesia doesn't handle well at all. And I wouldn't do it again. I mean, around the time I left EE, we were trying to swap this out for React. I think that was the right thing to do. The reports I hear are that actually React solved that problem. So yeah, don't use Amnesia in use cases where it's write-heavy. So yeah, I mean, replicated read-heavy is OK, like I mentioned. Or standalone write-heavy is OK too, to a certain extent. Because Amnesia on a single node fares pretty well. You can make it work. But if you combine the two, it's just asking for trouble. Hot code loading, again, a very useful feature of Erlang. But there are a few things to take into consideration. I mean, if you're running a couple of nodes or a handful of nodes in production and you want to upgrade the code on it, you can do it by hand and you can sort of manually manage the thing. But there are a few things to think about when you're using hot code loading. That is the process state management. I mean, when you load a new version of the code, how do you upgrade a state from old to new? And if something goes wrong and you want to roll back, how do you roll back the state as well? And the bigger thing is, I guess, traceability, as in, if you keep patching individual nodes with individual beam files, you need a mechanism so that for any given node, you can say, well, this beam file came from this point in the source tree. If you can't do that, then, well, it's asking for trouble, like I said, beyond a certain amount. I mean, a handful of nodes you can probably manage, but if you're talking tens or hundreds of nodes, if you don't have the ability to trace back a beam file back to your source repository, then you get into trouble. So the advice is don't use hot code loading to patch your systems unless you've got automated installation and rollback scripts, because even for tens of nodes, rolling back one node at a time is actually asking for trouble as well, because what happens is as you are rolling back, half your system is in the upgraded state and half in the rollback state, and your shared state becomes really messed up. And TCP sockets, the advice is don't use active true mode on sockets in production. I mean, this should be fairly, I think it should be obvious to most people who use Erlang for anything serious, but I'm just putting it down for the record. Active ones is the safest one, where basically you're asking the socket every time, give me a message. So you have full control over how many messages you're taking off the socket. But I recently discovered actually that using active ones, we saw performance degradation, and this is when moving from Red Hat Enterprise Linux 5 to 6. I was quite surprised by that, and actually digging into it, well, I suppose in retrospect it's obvious, but every time you read from a socket, there's a spin lock being acquired in the kernel, and that was killing performance for us. I still quite haven't got to the bottom of why it wasn't a problem in a previous version of the operating system, but I'm still working on that. But we worked around that by using ActiveN, which is basically you can say, well, instead of saying to the socket, give me one message at a time, you can say, well, actually, give me 100. And so the worst case, what you can have is from your socket, you're getting 100 messages dumped into your process message queue. But that's still manageable. And once you've processed through that 100, you can then say, right, give me the next batch of 100. And that actually is giving us the highest performance at the moment. And yeah, I mean, with Erlang, it's important to think about the overall system design as well. Because what I found is, I mean, when you're prototyping, it's fine to bung everything into a single node and say, you know, I'll just get it working first. And you don't really pay much attention to how you're splitting responsibilities between nodes. But what I found works best is that if you make each Erlang node as independent as possible, and that also means not doing amnesia replication in anger, then it works really well. Each node should really be an independent unit of computation so that you can actually scale out. So here's an example of a system which, again, is badly designed from an Erlang point of view. So basically, you've got data feeds coming in, and we had 18 of these nodes, and they were all exchanging state with each other. And if node 1 went down, data feeds all migrated on to, say, node 2. And the data feeds were not small. That's tens of thousands of messages a second. I like to call it a distributed monolithic system. Even though we had 18 nodes, if one of them died, it caused a domino effect. The next one would get overloaded, that would die, and eventually the whole thing would die, which sort of defeats the whole purpose of using Erlang. So a better way is to give each node an independent unit of work, and then have a sort of a distributor or a load balancer, so that you're handing out partials of work, and each one does it really well and behaves predictably. So to recap, prefer lots of short-lived stateless processes over a few long-lived ones. Beware of message queue buildup in Erlang processes. Beware of native RPC limitations. Again, like I said, if you're dealing only with the hundreds of, or even a few thousands of messages a second, you'll be fine with native RPC. But if you're running into tens of thousands of those, it will not work. Amnesia is awesome, but only for certain use cases. ActiveN works best for TCP sockets, and overload control is not optional. If you're running at scale, you really need to do overload control at the edges. So yeah, and a brief word about open source efforts at Bet365. We are working on better ODBC support. We have a lot of SQL databases in our business, and we'd like to be able to access them from Erlang, but the ODBC support is is not great at the moment. So we're working on that, and we will open source it at some point. We're working on a proper SOAP implementation. The SOAP support in Erlang is non-existent officially, and whatever open source stuff you can get is very hackish, and you need to know the right spells to make it work. And we're also assisting in Ericsson in developing a package manager for Erlang. So yeah, that's the end of it. Any questions? Yeah, I mean, Yeah, so the question is, did you ever make use of OTP? Well, yes, I mean, OTP is being used extensively purely because of how much it simplifies the writing your code. I mean, supervisors and gen servers are what get used most. But yeah, without OTP, I think it would be quite hard to build complex systems in Erlang. Any more? No? Okay, thank you very much.